Now we will try to understand what are diffusion and effusion. So first of all, let's write down the definition of diffusion. When two or more gases are allowed to mix in a container, then due to the random motion of the molecules, intermixing takes place. And this is called diffusion. And if we talk about effusion, effusion is when gas molecules are allowed to move out through a pinhole, as you can see in the figure. And this movement is towards the low pressure region. Let's just highlight this a bit. Okay, the movement in effusion is from a high pressure region to a low pressure region, and this process is known as effusion. Now, some important points to be noted are that the molecules move from higher concentration to lower concentration. And also another point is that the lighter molecules diffuse or effuse faster than the heavier counterparts. Now, if we look at the figure, we can observe that diffusion is basically, we have these orange molecules on the right hand side and these blue molecules on the left hand side. And diffusion is when both of them are intermixing, like you can see in this region. And this intermixing happens because of random motion of the molecules. And similarly, in effusion, we can see that we have a pinhole here and the molecules are traveling from their region of higher concentration to their region of lower concentration, right? The motion is in this manner, and this is known as effusion. So now, since we know what diffusion and effusion are, we'll move on to the Graham's law of effusion. So let's first write the statement of the law. What does it say? The Graham's law states that at constant pressure and temperature, I am referring to them as P and T respectively, the rate of diffusion or effusion is inversely proportional to the square root of the density. What does it mean? That the rate, let's call it R, the rate is inversely proportional to 1 by square root of density. And if you refer to our lecture from the ideal gas part, we know that the expression from density is Pm divided by RT. So at constant pressure and constant temperature, we can say that the rate is also inversely proportional to square root of the molecular mass of the gas. And it is also inversely proportional to the square root of the vapor density, if we are talking in terms of vapor density. So consolidating all of these, we can say that the rate is proportional to the pressure. This is something which is quite analytic, that if you have a higher pressure on one side, the motion would be from the region of higher pressure to a region of lower pressure. We had studied that in effusion. So the rate is proportional to pressure and inversely proportional to square root of the density, or just write it as the molar mass, and it is directly proportional to the area. Let's think of it in this way, that if we have a pinhole of this size and a pinhole of this size, a smaller size, the rate of gases effusing out would be higher for a pinhole of a higher area, right? So it is also directly proportional to the area. And if in the case when the temperature is not constant, like we're talking only about the rate, not about the Graham's law. So when the temperature is not constant, we observe that the rate is also inversely proportional to the square root of the temperature. So this is what becomes the entire expression which is generally used for rate. Also, the rate can be defined in a number of different ways, such as it would be the length traveled by the diffused gas upon the time. How can we represent this? Say we have a tube here and this is the pinhole, right? So the gas will be traveling in this manner. So we calculate the length that the gas traveled per unit time. That can be defined as rate. Another thing which can be defined as rate is the volume of the diffused gas per unit time, right? Or similarly, the number of moles of the diffused gas per unit time. So these are some important expressions inside this highlighted box, which would be nice to remember and solve questions.